Okay, here's the setup. We want to find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate plane, so meaning sitting on the floor, the side, and the back, and 1 vertex in the plane x plus 2y plus 3 is equal 6. So we're going to draw a little picture. So here's our 3-dimensional coordinate system, x, y, z. And to kind of graph this plane, what we're going to do is we're just going to say, well, I know that my x-intercept is going to be 6, because these are 0, x is 6. My y-intercept is going to be 3, and my z-intercept is going to be 2. So my z-intercept is 2, 0, 0, 2. My x-intercept is 6. Doesn't really have to be a perfect picture. And my y-intercept is 3. And then we just connect the dots. There's our plane. And then the corner of the box that's kind of the opposite corner from the origin sits on this plane somewhere. So maybe it's like, maybe it's like, this way, and then this way, and then this way. And maybe that corner is on the box. So, you've got kind of this deal here. I haven't drawn this perfectly, unfortunately. Yeah, so that's where my drawing skills are bad. Sorry. So like this. Like that. So there's a little box. And that corner is on this plane x plus 2y plus 3z equals 6. So let's label the dimension of the box. This side is x, this side is y, this side is z. And the volume, which we're trying to maximize because we want the largest box, is x times y times z. But this point is on this plane. So our constraint is that x plus 2y plus 3 is equals 6. Or I might solve for x and say x equals 2y plus 3. Let's start with x plus 2y plus 3z equals 6 and solve for x and get x equal to 6 minus 2y minus 3z. We could have solved for z to make it more normal and have a function of x and y, but it's really fine to do whatever's easiest. So now if we plug this in for x over here, we're going to get volume as a function of y and z, which is totally fine. That's going to equal 6 minus 2y minus 3z times y times z. And so if we multiply this out, our volume as a function of y and z is going to equal, let's see, 6 times y times z, 6yz minus 2y, y is 2y squared z minus 3yz squared. And then we're going to do the usual thing. We're going to take the partials, we're going to set them equal to 0 to find the critical values, critical points, and then we'll see if we have a max or minimum. So let me make sure you can see this. I should, let me just pull this up over here so I can see this better. Since no one's looking at it, I might as well just pull this up over here and do a new share of my visualizer. Great. That way I can see what I'm looking at a little more easily. You all can kind of see me a little more easily. 1 second. Yeah, maybe. Okay, is that better? Sure, probably. All right, cool. So finding the first partial with respect to y. So I'm using y and z since my function is a function of y and z. So vy is going to be, let's see, 6z minus 4yz minus 3z squared. And set that equal to 0. And then I'm going to get vz equal to 6y minus, let's see, 2y squared minus 6yz. Whenever you're saying things like this equal to 0, it's good to try and maybe look for the easier one, although these both look about the same amount of complicated. So we try to factor something out. From this first one, I say I can factor out a z. I'm left with 6 minus 4y minus 3z equal to 0. So I could get z equal to 0, which isn't a good answer because, right, we don't want a box with a length of 0 or height of 0. Or we could get this equal to 0. So I see 6 minus 4y minus 3z equal to 0, or I'd probably write this as 6 equal to 4y plus 3z. And I'm probably going to end up solving for one of these variables here. Same idea here. I can factor out a y. I'm left with 6 minus 2y minus 6z equal to 0. I can either get y equal to 0, which again, I don't want. I don't want a box where one of the dimensions is 0. Or I can get 6 minus 2y minus 6z equal to 0. So what I would probably do here is maybe solve for y. So I'm going to say that 6 minus 6z equals 2y. And then y is going to equal 3 minus 3z. I can plug that in over here and get that 6 is equal to 4 times 3 minus 3z. That's the y I'm plugging in, plus 3z. So 6 equals 4 times 3 is 12. 4 times negative 3z is minus 12z plus 3z. So 6 minus 12 is negative 6, and negative 12z plus 3z is negative 9z. So it looks like z is equal to 6 over 9, or 2/3. We plug that back in for y over here, and y is going to equal 3 minus 3 times 2/3, which is just 3 minus 2, which is 1. I personally would go back, and so what we could, I keep on looking over there. What we could do at this point is go back and say, well, we can just plug that into our volume equation here and find what the volume is. I kind of like knowing the dimensions too, even though this question doesn't ask for the dimensions. I would probably go find x and say x equals 6 minus 2y minus 3z. So x is going to equal 6 minus 2 times 1 minus 3 times 2/3, which is going to be 6 minus 2 minus 2, which is going to be 2. So x equals 2. And then we can just multiply those together to get the volume. So the volume is going to be x times y times z, which is 2 times 1 times 2/3, which is 4/3. I should point out, right, sometimes a question like this will ask you for the dimensions. And so the dimensions would be, a box that was, say the dimensions were inches, right? 2 inches by 1 inch by 2/3 inches. Sometimes they ask for the maximum volume, which is 4/3. Oh, you know what I didn't do? I didn't check to see that it was a maximum. So let's do that really quick. That's because that's something that you really shouldn't have to do, but it's good to do just in case. So if I was going to check to see if it was a maximum, I kind of ran out of room here, unfortunately. So let's go look at our first partials. Our second partials are going to be VYY, which is, let's see, 0 minus 4z minus 6z, minus 0. And then VZZ is going to be derivative of that 0, minus 6y. And then the mixed partial VZY is going to be, let's see, 6 minus 4y minus 6z. That's the same as VYZ. It should be, let's see, VYZ would be 6 minus 4y minus 6z. Got it, checks out. So then our gamma of y comma z instead of x comma y is going to be this times this minus that squared. And now if we're going to plug in our critical point, which was y equal to 1 and z equal to 2/3, our gamma value is going to give us, let's see, we're going to get negative 4 times 2/3 times negative 6 times 1 minus 6 minus 4 times 1 minus 6 times 2/3 is 12/3, which is 4 squared. So let's see, this is going to turn out to be negative 4 times 2. We actually have to do the multiplying here to see what's so. Let's see, negative 4 times 2/3 is negative 8/3 times a negative 6 is positive 48/3, which is 16. Or we could have canceled. We could have canceled here and said that's a negative 2, and then right. And then minus 6 minus 4 minus 4 is negative 2, and negative 2 squared is 4. So that's 12, which is positive, which means we have a max or a min. So max or min. We want it to be a maximum, but we need to check. And when we look back and check, our second derivatives are both negative, right? VZZ is negative 6y. If we plug in y equal to 1, that's 6. That's going to be negative 6, which is negative. So we're concave down, which means we have a maximum. Again, typically, you don't have to actually check this if you're only getting, if they're asking you to find a maximum and you're only getting one critical point. It's usually a pretty standard situation that you're going to be getting what you want, but it's probably good still to practice actually getting the thing you're looking for. Let's look at one more example like this, and then we'll actually do two more examples, and then we'll talk about one more thing. So yeah, this is a good example. We want to find the shortest distance from the point 2, 1, -1 to the plane x plus y minus z equals 1. And notably, right, the point isn't on the plane. So this plane, again, the way I usually draw a plane, if it doesn't go through the origin, is just by graphing all the intercepts. So this plane, I'm going to try to graph it. Here's my z-axis, x-axis, y-axis. So looking at this, if my x-intercept is going to be 1, my y-intercept is going to be 1, and my z-intercept is going to be -1. So I've got something looking kind of like this. So I will tell you, I'm not the best at drawing. Here's my plane. Oh, yeah, maybe. Again, that's just part of the plane, right? It really kind of keeps going. And then the point 2, 1, -1 is 2 in the x direction, 1 in the y direction, and 1 down in the z direction. So maybe it's like over here. And we're trying to find some point on the plane so that it is that point on the plane is the closest to that point there. I'm going to call that point, since I don't know it, I'm going to call it x, y, z. And if we're trying to find the point on the plane that is closest to this other point 2, 1, -1, what we're really trying to do is minimize. Right, so this shortest distance means we want to minimize the distance between the unknown point x, y, z and the point that's not on the plane 2, 1, -1. So I realize I worded this kind of the way that makes it more obvious, right? It says find the shortest distance from the point to point 2, -1, 2, 1, -1 to the plane x plus y plus minus z equals 1. But the way this is often phrased is find the point on the plane that is closest to, and then you have to realize, oh, if we're finding the closest point, that means we have to minimize the distance between the points. So if we're minimizing the distance here, we want to minimize this, the square root of x minus 2 squared plus y minus 1 squared plus z minus -1 squared. Here's a very, very useful piece of information. Whenever you're trying to minimize a distance between two things, you can actually minimize the square of the distance. So instead, we're going to try minimizing the distance squared, which is the square root, which is not the square root, but I'm going to write it anyway. So x minus 2 squared plus y minus 1 squared plus z plus 1 squared, which is just x minus 2 squared plus y minus 1 squared plus z plus 1 squared, which is usually going to be easier to deal with. So typically, instead of minimizing something that has a square root like this, you can almost always minimize the square of it, because what you're doing essentially is you're saying, well, I want to make this as small as possible. Well, really, I want to make this as small as possible. But if I make the insides as small as possible, and they still have to be positive because the distance between 2 points can't be negative, you make the insides as small as possible, then the square root of that will also be as small as possible. Always works. Pretty great. Then we need our constraint. And our constraining piece of information is that this point has to be on this plane. So we have the x plus y minus z equals 1. And here I would kind of make the usual choice and isolate z. So I'm going to say that z is equal to x plus y minus 1. Essentially, I brought the z over to the right and the 1 over to the left. And I'm going to plug that in here. So I'm actually trying to minimize the distance squared equal to x minus 2 squared plus y minus 1 squared plus, let's see, x plus y minus 1 plus 1 is just going to be x plus y minus 1 plus 1 cancels squared. And that is going to be the function of x and y that I'm going to try to minimize. Take the partials. We're going to use the chain rule, kind of. Now we're going to use the chain rule. So fx is going to be the derivative of x minus 2 squared. Well, the derivative of some stuff squared is 2 times my stuff to the first power times the derivative of the stuff, but that's just 1. Derivative of y minus 1 squared is 0 because there's no x's there. And the derivative of x plus y squared is 2 times my stuff, 2 times x plus y to the first, times the derivative of this stuff, which is just 1 plus 0. Again, not really necessary to write, but so that's going to be, if I multiply it out, 2 times x minus 4 plus 2x plus 2y. And we want that to equal 0. Great, we'll deal with that in a minute. We get fy, same kind of deal. Derivative of that's going to be 0. Derivative of that's going to be 2 times y minus 1. Derivative of that's going to be 2 times x plus y. And if we simplify that, we get 2y minus 2 plus 2x plus 2y equal to 0. And then we kind of have to combine these together. I would probably isolate one of the variables in one of these. So let's see, looking at this, I would probably go ahead and say, let's see, sure. So here I can take this first one and rewrite it as 2y on the left equal to, on the right hand side, I'm going to get a plus 4 and a minus 4x. Or in other words, y equals 2 minus 2x. And I'm going to take this other equation, which I'm going to simplify just a little bit as, so this is my, I guess I'm using my fx here. And then for my fy equal to 0, I'm going to simplify a tiny bit and write this as 4y plus 2x equal to positive 2. And I'm going to plug this in for y here. I'm going to get 4 times 2 minus 2x plus 2x equal to 2. So then 8 minus 8x plus 2x equal to 2. So negative 6x equals negative 6. So x equals 1. And then plugging that back in here, y equals 2 minus 2 times 1. So y equals 0. And then plugging that back in so I can find the other coordinate, because I like to know the coordinates, even if they're not asking for that. I know that z equals x plus y minus 1. So I'm going to get z equal to 1 plus 0 minus 1, which is 0. So the closest point is the point x is 1, y is 1, and z is 0. X is 1, y is 0. I think I said 1, but I meant 0. So the x-intercept happens to be the closest point to the point 2, 1, negative 1. And more importantly, to answer the question that was asked, which is to find the shortest distance, we're just going to take those points and plug them into this distance formula here. Not the distance squared, because they asked for the distance. So the distance is going to equal the square root of x minus 2 squared plus y minus 1 squared. Okay, so plus z plus 1 squared. So actually plugging in, we're going to get that the distance is equal to the square root of, let's see, x is 1, so 1 minus 2 squared, y is 0, so 0 minus 1 squared, and z is 0, so 0 plus 1 squared. So it's a little messy there. That's going to be the square root of 1 plus 1 plus 1, which is the square root of 3. So that is the shortest distance between this point over here that's not on the plane and the plane. So specifically, it's the distance from here to there, because that's the point we found that was actually the closest. It won't usually be an intercept like that. It just happens to be in this example. Okay, let's look at one more, which is going to kind of lead us to something new. So here's kind of a classic example. It's probably in the textbook somewhere. We want to find the dimensions of the largest rectangular box by volume. So typically, I should point out, when someone says the largest something, if you're talking about a three-dimensional shape, we mean the most volume. If you're talking about the largest, like, two-dimensional shape, we mean the most area, kind of like that. So whatever dimension, the biggest dimension that the thing exists in. So find the dimension of large box, rectangular box by volume that can be mailed under the US postal system requirement, that the length plus the girth must be no more than 108 inches. Okay, so let's draw a little picture. The length is going to be the longest dimension of the box. That's typically how the post office is thinking about it. So let's call this, let's still use X, Y, and Z. So let's call this Z, this X, and this Y. So Z is my length. And then the girth is kind of the around part. So I'm going to draw it here, right? If this is your length, then the girth is this. Essentially X plus Y plus X plus Y. So the girth is 2X plus 2Y. Or basically whatever your not length dimensions are, 2 times each of them added together. And we want to maximize the volume, which just like in the first problem we did today, the volume is going to be X times Y times Z. And as is typical, we have a constraint. So in the first problem we did today, the constraint was that the corner of the box had to be on this plane. Here, the constraint's a much more real thing. It's that we are limited by the length plus the girth being less than or equal to 108. Now, since we want to maximize the volume we can contain, we're going to set it equal to 108. We're going to use up that full constraint value. So we're going to say that the length plus the girth is equal to 108, or in other words, Z plus 2X plus 2Y is 108. So there's the thing we want to maximize. There's the constraint. As is typical, the thing we want to maximize is a function and it's not equal to a number, whereas the constraint is some equation that equals a number that allows us to solve for one of these variables. So let's solve for Z. So Z is going to equal 108 minus 2X minus 2Y. And then we're going to plug that into our volume and have a function of 2 variables, right? Because here, right, the whole thing is, wait, this is a function of 3 variables. We can't do the thing yet. So we're going to take that and we'll be like, okay, now our new volume is going to be, as a function of X and Y, X times Y times this, 108 minus 2X minus 2Y. And it's definitely, you could do a triple product rule, or actually just a product rule to take the derivative of this, but we shouldn't. It's way easier just to multiply it out. So our volume as a function of X and Y is 108 XY minus 2X times XY is 2X squared Y minus 2XY squared. As I have mentioned before, this function, lots of our functions, happens to be symmetric in the variables X and Y, meaning if you interchanged X and Y, this equation will still be the same, right? If I interchange X and Y, I'd have 108 YX minus 2 Y squared X minus 2 YX squared, which is exactly the same equation. When that's true, it usually means that the X and Y values that we find will end up being the same. So just something to be aware of. I'm expecting to get X and Y equal to the same number. All right, let's take our partials. Vx is going to be 108y minus 4xy minus 2y squared. And again, I see I can factor out a y. I can actually factor out a 2y. If I factor out a 2y, something is equal to 0, I'm going to get 108 divided by 2 is 54. I'm left with a 2x and a 1y there. I don't want this equal to 0. That's not helpful. But setting this equal to 0, I'm gonna isolate y and get y equal to 54 minus 2x. I set that equal to 0. Let's do the same thing for Vy, so partial with respect to y, should give us kind of the same result. So I'm going to 108x minus 2x squared minus 4xy. Notice how these partials are essentially the same, just with x and y interchanged because we have symmetry. If we set this equal to 0, factoring out a 54, sorry, not a 54, a 2x, we're left with a 54 minus an x minus a 2y. Instead of setting, right, so I could do the same thing and solve for x here and get x equals 54 minus 2y. That's not actually helpful though. What's more helpful is just to set, right, we don't care about this being 0. Not helpful, but we could set this equal to 0. And then plug in this y over here. So then we're going to have, and it might get a little bit messy here, 54 minus x. I should just use another piece of paper because I'm going to have to anyway. Minus 2 times 54 minus 2x equal to 0. Okay, simplifying this out a bit, I'm going to get, let's see, 54 minus 2 times 54 is minus 108, and 54 minus 108 is going to be negative 54. So we're going to end up getting negative 54, and the negative x, a minus 2 times a minus 2x is a plus 4x, so the negative x plus 4x is a plus 3x equal to 0. So 3x equals 54, or x equals 18. And then looking back over here, I'm going to get y equal to 54 minus 2 times 18. 54 minus 36 is also 18. No surprise. We were already expecting x and y to be the same. So then we could go and check. We probably should check that it's actually a maximum. So we're going to take our second partials. Vxx is, let's see, 0 minus 4y, 0. And vyy, I'm expecting to get negative 4x because of symmetry, but let's check. Vyy is 0 minus 4x, yep. And Vxy is going to be, let's see, 100, so Vx is that, so is 108, ooh, it's big, minus 4, that's good, that's kind of a lot, minus 4x minus 4y. Is it the same the other way? Let's double check. Vyx should be 108 minus 4x minus 4y, checks. Okay, so then our gamma here is going to be negative 4x times negative 4y minus this gross thing, which again, it might work. It might be an interest to factor out the 4. To factor out the 4, 108 divided by 2 is 54. 4 divided by 2 is 27. So divide by 2 twice, you're dividing by 4. So that's going to be 27 minus x minus y squared. If I plug in my critical point, which is 18, 18, I'm going to get, ooh, that's going to be big. 2 times 18 is 36. So 4 times 18 is 36 times 2, which is 72. So negative 72 times negative 72 minus 4 times 27 minus 18 is 9. Minus another 18 is negative 9. All right, so that's 36 squared. That's 72 squared. 72 squared is bigger. So this is this number, 72 squared, and this number is 36 squared. I'm ignoring the negative signs because when you square a negative, I guess I could say it's negative 72 squared and negative 36 squared, but that's certainly bigger than that. So this is going to be positive. When it's positive, you know you have a max or a min. So then we go back and check to see, oh, but my second partials are both negative, right? My Vxx at 18, 18 is negative 72. I don't really care what the number is. I just care that it's negative because that means we are concave up. So we have a, sorry, not concave up, concave down. Apologies. That's silly. That means we have a maximum, not a minimum. So yes, we have a maximum volume when x equals 18 inches, y equals 18 inches, and oh, we need to find z still. So if we go back and look at our previous work, z is equal to 108 minus 2x minus 2y. So z is going to be 108 minus 2 times 18 minus 2 times 18, which is 108 minus 36 minus 36, which is going to equal 36. So Z is 36 inches. These are the dimensions of the box with maximum volume that meets the constraint that the length plus the girth is less than or equal to 108 inches. Cool. Okay. So the reason I really want to talk about this example is because there's another way of approaching it. And it's a good example to kind of bring us into what is known as LaGrange multipliers. So there's a couple different ways people talk about this. And since no one is in class today, nobody's here to tell me if your professor is going to do this a slightly different way. So I'm going to do it kind of the standard way. And then if we need to adjust, we'll adjust. And I'll kind of talk about how really all the ways are the same, it's just slightly different. So let's do the same problem, except now we're going to use LaGrange multipliers. So again, same problem. So I don't really want to write it, but I will. So find the dimensions of the largest rectangular box. And I'll just write the constraint whose length plus girth is less, I should say no, it's easier to say no more than, instead of less than or equal to, is no more than 108 inches. So same box or same looking box. Now we know what the answer is already. Right? We know that the answer is going to be that X and Y are both 18 inches and Z is 36 inches. Obviously, I'm not drawing my box to look like what I know the answer is, but that's going to be the answer. Okay, so here's the setup. We want to maximize volume equal to X times Y times Z. And our constraint is 2X plus 2Y plus Z equal to 108. So what we typically do with LaGrange multipliers is we call the function that we're trying to maximize capital F. So this is my capital F of X comma Y comma Z. And we call the constraint capital G. Now there's a couple of ways people do this. And I'm trying to look here and see if Grant has done it in a specific way. Nope, not really. So I feel like in 16C, the usual standard way to do this is to say, I'm actually going to solve this by setting it equal to 0, although really setting it equal to any constant is actually fine. So you could have 108 over here, or you could have 0 over here. It doesn't really matter. So you can use this, or you can use this. 2X plus 2Y plus Z minus 108 equals 0. So some people like to say that this is my function G of X comma Y comma Z. Some people prefer to say this is my function G of X comma Y comma Z. It doesn't actually matter because we're going to be taking the partials of G, and the partial derivative of G doesn't care if you have an extra 108 over here or not. So here's what we're going to do. We're going to take, well, and so again, I'm trying to be very I'm trying to show all the work here. So some textbooks then define this, oh yeah, some people do this weird. So people call this little f or little g. But basically what we do is we say, I'm going to define, no, I really don't like doing it that way. Here's the breakdown. So you can do this thing where, yeah, I'm sorry, I'm going to make this a little bit more clear or less clear maybe. Sometimes people call this little f. People call this little g. So here's one way of approaching this. We're going to set the partials of f equal to a multiple of the partial of g, meaning I'm going to set the partial of f with respect to x equal to lambda times the partial of g with respect to x, and also the same for y and z. So I'm going to set the partial of y equal to lambda times gy and the partial with respect to z equal to lambda times gz. There's a reason for this whose explanation is kind of weird. We can definitely get into it if you want to, but I don't really want to right now. So the idea typically is to use these equations to then solve for, well, we'll see here. So let's find them. So fx is going to be, well, the partial with respect to x is going to be yz. And gx, the partial with respect to x, is going to be 2. Here, the partial with respect to y is going to be xz, and the partial with respect to y for g is going to be 2, so lambda times 2. And here, the partial with respect to z is going to be xy, and the partial with respect to z is going to be 1, so lambda times 1. And then what is typical is to isolate lambda in each of these and then set them equal to each other in a way that allows you to solve for, well, solve for x, y, and z. So for example, if I set these two equal to each other, or if I really solve for lambda first, so yz over 2 equals lambda, xz over 2 equals lambda, and here we have just lambda equal to xy. Setting these two equal to each other, right, because they're both lambdas, allows us to get, well, I've got yz over 2 equal to xz over 2. I can cancel the 2's and cancel the z's and get y equal to x, which we know is true. We know from our previous work that we just did that y doesn't equal x. And then picking either one of these with this one, so maybe using these two that are closer to each other, if I set xz over 2 equal to xy, well, multiply both sides by 2, divide and cancel the x's. So I essentially get z equal to 2y. And now that I have y, x in terms of y and z in terms of y, I can go back to my constraint, which was 2x plus 2y plus z equal to 108, and I can plug these in. I can plug in y for x, and I can plug in 2y for z. So basically, the idea in this process is to use these equations to allow you to get each of two of the variables in terms of the third variable, and then plug those into the constraint equation, so that then you can say, oh, I've got 2 times y plus 2 times y plus 2 times y equal to 108. 6y equals 108, and 108 divided by 6 is, you guessed it, 18. Which means then x is also equal to 18, which then means, oh, z is also equal to 2 times 18, which is 36. Just like it was in the previous version of this problem where we did it the regular kind of way. One thing I will, so what I will say is LaGrange multipliers doesn't actually tell you if you have a maximum or minimum, which is kind of a downside to it, but it is a pretty useful method, which we'll see in more examples later on. The last thing I want to say is that, so some people just do it like this, where you say this is f and this is g, and you set each partial equal to each other. Some books, teachers like to make it more complicated, I feel like, by doing the following thing. So here's what some people do instead, and this is why I use the lowercase letters, because we use capital. So some books go ahead and say, well, I'm going to call, and I'll do it in red to kind of match with the red I've used. So I'm going to call this little f and this little g, and then we're going to define a new function, capital F of x comma y comma z comma lambda, and it's going to equal little f minus lambda times g. So in this particular case, it's going to equal little f, which is just x times y times z, minus lambda times little g, which you can either call this or this. It doesn't matter. Most books, I think, call it this when they do it this way. So that's going to be 2x plus 2y plus z minus 108. And then we're going to find all the partials. So capital Fx is going to be yz minus lambda is a constant, and we're going to get lambda times the derivative of this with respect to x, which is just 2. So we're going to get a 2 lambda, and we're going to set that equal to 0. And then fy is going to equal the partial with respect to y, which is xz minus, again, the lambda hangs out, and the derivative of this with respect to y is 2. And then fz, partial with respect to this part, is going to be xy. Partial with respect to this is going to be 1 times lambda, so equal to 0. And lastly, and this is the part that seems silly to me, and you'll see why in a minute, I'm going to find f lambda, which is going to be, well, let's see, the derivative of all this is 0 with respect to lambda, and the derivative of lambda is going to be a -1 times 2x plus 2y plus z minus 108 equal to 0. And the reason this is silly to me is because this is really just the constraint again. So this here, let me move this out of the way because it's kind of in the way. This is just the constraint again. Right? If you multiply sides by -1, you just get 2x plus 2y plus z minus 108 equal to 0, or 2x plus 2y plus z equal to 108. So I find it kind of silly to even do this. What I want to point out here is that these equations are exactly the same as these equations over here, right? I've got yz minus 2 lambda equal to 0, or in other words, yz equal to 2 lambda. Same as I had over here. I've got xz equal to 2 lambda. Same as I had over here. And I've got yz equal to, or sorry, xy equal to lambda. Same as I had over here. So whichever way you do this is totally fine. You end up getting the same stuff. I find it typically easier. You think of it this first way, where I'm just saying, this is f, this is g, take the parcels of f and set them equal to lambda times the parcels of g. But some people find it more convenient to kind of build this new function as your thing you want to maximize minus lambda times your constraint, and then find all these partials and then do the same sort of work. The work is still the same. You typically isolate lambda and then set different pairs of lambdas equal to each other to allow you to solve for x, y, and z. All right, we'll talk more about Lagrange next time. I hope this was illuminating.